Hi everyone. Today I'm going to present on topic in-memory computing architecture for Tsetlin machine inference using MTJ-based Crossbar. So, so what is a computing architecture in first place? So, a computing architecture consists of a processing unit and memory. So these two connect using a bus, and we primarily use one human model, and this model uses computing architecture and memory units in different positions, and they are connected using bus. So this is the present model of computing architecture, and the disadvantages with this particular model is that there are limited number of buses, and buses are not very fast. So because of that, the memory takes a long time to transport from here to the CPU. So there is a memory bottleneck, and also it takes time to reach from this part to this part. So when computation unit needs memory, it requests the memory to send the data, and it takes time to reach that side and from memory back to the computing unit. So because of that, there will be latency. And let's just say there is heavy amount of data that you need to process in the computation unit. Then for that data processing, it is inefficient to send it through buses every time. So because of these disadvantages, we want to introduce a new computing called in-memory computing. And in in-memory computing, we bring the memory directly into the computation unit. So there won't be any buses to get the data from memory to CPU. So in-memory computing, we get the memory and CPU in the same point and in the same place itself. So what it does is strategically organizes computations to leverage parallelism and locality, addressing the constraints of the von-Neumann bottleneck. So that is in-memory computing. And the next prerequisite that we need to know before we get into the architecture is Tsetlin machine learning. So we know different machine learning algorithms that exist like neural networks and different other things. So the main disadvantage with those machine learning algorithms is that they are not interpretable and they are not explainable machine learning algorithms. So they are often called as black boxes. But our machine learning algorithm, Tsetlin machine learning, is not like that. It is a classification algorithm, and it is not a black box, and we can completely understand and interpret it. So it eliminates the black box nature of neural networks. And the learning unit in a Tsetlin automata, in the Tsetlin machine, is called a Tsetlin automata. And Tsetlin automata is similar to a finite state machine and contains multiple states, and multiple states can be moved through in different fashion as shown in this by these arrows. And based on the training data, we are going to train this Tsetlin automata for every feature, and every feature has a Tsetlin automata, and after training we get the feature as either 0 or 1. So basically the whole feature is trained over whole data set, and we finally arrive at a particular action value for every feature, and action value can be 1, also called as include, and action value can be 0, also called as exclude. So based on this, let's get in next slide. So yeah, so based on this, we can get the inference in the following way. So first of all, we store all the Setlin automata actions that we found here, found by training a Setlin automata, and then store it here as shown in the diagram, And we need to test this particular train data with some input features. Let's just say this is our input features. Then this input features is given in binary form and its complement form also. 0 will give 0 and 1, 1 will give 1 0, 0 0 1, 1 will give 1 0. So these will interact with the Tsetlin automated trained data. So the interaction happens in the following way. There will be a NOT gate, there are OR gates and some AND gates. So this is the whole computation that is required to arrive at the final value, and this final value will tell whether our particular input 4.6 whatever that is belongs to the particular class or not. So since this is a classification example, if we get one, then it could be the same class. If it's 0, then this particular features doesn't imply it's in the same class. So the steps for doing a whole thing is we just booleanize these input features, we generate the boolean literals of feature and its complement. So we generate feature and its complement here, and we generate train literals of features which are given in the right side as shown here, and we do the OR operation of input literals with complement of train literals. So self-explanatory as shown here, and we do the AND product of all of this to get the final output which determines the final class it belongs to. So the next step after this is class computation. So this particular compute unit is called a class, and there are multiple class that we need to compute, and then we have to add all the values that we get from the clauses, and which class gives the maximum value will tell which class that particular input belongs to. Let's just say class M gave class M the highest among all the other classes, then the particular input belongs to class M. Okay, so the class outputs are added, and the highest outputs decides the classification output. And come into the problem with this inference mechanism. So in this inference mechanism, we are using and OR gates, and because of multiple and huge usage of this and OR gates, there is high power consumption for it, and further we have to store the train data in memory, and for that purpose we need to shrink the memory for high density, and we can't continuously scale the CMOS based memories, and we would reach a point where it cannot be scaled down. So that's one problem, and also the computation speed is low because we need to get the, as shown in the diagram, we need to get the inputs from the memory block, and we have to get it to the compute unit and then compute with it. So every time getting the data from input memory will take time, and because of that the computation speed is low. So the solution that we are coming up with is in-memory computing. So in in-memory computing, we can scale down the memory units, and we can have high density arrays of memory in one particular little space. So in-memory computing is a great technique that can tackle all these challenges. And we have to choose a good memory unit which helps all of this. And the memory unit that we chose for this is magnetic tunnel junctions because of its high density production in a silicon chip. So let's learn about magnetic tunnel junctions. So this is the magnetic tunnel junction that we are working with, and this can be simplified in the below diagrams, and these are the main layers, three layers, and the remaining and everything are just other layers for protection and other things. So these are the three layers that we need to focus on, and the bottom layer is called pin layer and the top layer is called free layer. Okay, and pin layer, the magnetic state or magnetic direction of it is fixed, and the free layer you can change the direction to either be in the same direction as the pin layer or be in the opposite direction of the pin layer. So we can have two different ways of arrangement of this free layer. So this gives rise to two stable states. So this is one state and this is the other state. This is called parallel state and this is called anti-parallel state because these two magnetic moments are in the same direction, so they are parallel state. If it's in opposite direction, it's called anti-parallel state. Okay, so this is a non-volatile memory storage, so it wouldn't go away after we store it, even though there is no voltage or any energy, it will stay there. So it is non-volatile in nature, mm, and this parallel state and anti-parallel state can be achieved by passing current through this. So if the current passed through this particular magnetic tunnel junction is greater than ICO, which is the critical current, if it is greater than the critical current and it flows in this direction through the free layer to the pin layer, then it will change to parallel state. If we give it in the opposite direction with current greater than the critical current, then this particular MTJ will turn into anti-parallel state. Okay, so we are getting two states from it. Okay, let's look at the IV characteristics of this particular memory. So from this IV characteristic, we can see that there is a transition between states at this particular voltage and also at this particular voltage. So these two voltages serve as the transition voltages. So giving a voltage of 0.2 volt or greater will set this particular MTJ to 1 or to 1 or also called as parallel state, and giving a voltage less than minus zero point 0.4 will bring the state to 0 and also called as anti-parallel state. Okay, so anti-parallel state we are representing the logical 0 and parallel state we are using it to represent logical 1. So by giving set voltage we are programming it to 1, and by giving reset voltage we are programming it to 0. So this is the way we program our particular magnetic tunnel junction. So with this introduction, let's look at the proposed inference architecture. Okay, so the proposed inference architecture uses 1T 1M cell. What is 1T 1M cell? 1T refers to one transistor, 1M refers to one MTJ. So they both are in series. So they both are in series and it forms a 1T 1M structure. So they must be programmed with appropriate actions. So how do we program them? We give different voltages at LK as we set voltage and we reset voltage, and based on that voltage we can set this magnetic tunnel junction to the required value from this. Okay, so the voltage pulse of specific duration and amplitude is provided at LK to program this Tsetlin automata cell. Okay, so now we got our memory element here which stores the train data. So now we need to do the computation between train data and our input literals. So to do that, we are using this inference architecture, And in this inference architecture, this particular square is the Tsetlin automata that we just discussed here. So this is the same thing as this square. So we give R L0, these are the laterals. So we give these inputs to LK and we get the output currents from every Tsetlin automata and add all those currents and send it to current sense amplifier. So we give our voltage here and then extract the current through this particular MTJ. Since MTJ is in different states, we get different currents. So based on the state it is in 0 or 1, we get different currents out of it, and these different currents are collected through this particular wire that connects all the Tsetlin automaton and gives it to this particular current sense amplifier. So this particular architecture works on Boolean to current mechanism, which means we are giving our input literals as 0 or 1 and we are collecting the currents from this Tsetlin automata which reflects the literal that we have given to the Tsetlin automata. So the computation between literal and Tsetlin automata, which used to be as logic gates, we are replacing it with currents. So instead of using logic gates, we are replacing with the Tsetlin automata and generating the currents and then collecting the currents and passing through the current sense amplifier. So after getting the current through the current sense amplifier, let's look at the current sense amplifier first. So this current sense amplifier has a back-to-back inverter and other transistors to charge this node and discharge this node. So this is one inverter and this is the other inverter, and this these three are to charge it. So during the partial clause evaluation or reading phase, our SE is connected to VDD. After connecting SE to VDD, we generate the currents and send it through this point, and this is the reference current. So if the collected current reaches a particular threshold, then we want out1 to be particular value, and if collected current is less than the reference current, then we want the output to a particular value. So that is done by this current sense amplifier. So the comparison between the currents between reference current and the collected current is reflected by voltages as out1 and out2 by this current sense amplifier. Okay, so this is the whole architecture. So let's look into the experimental results and the validations of this particular inference architecture. So the experiments or results. So let's start with the programming and computation of single Tsetlin automata. So let's take a single Tsetlin automata and we will try to change the state of that magnetic tunnel junction. So let's just look at this particular thing. So when we give a voltage of minus 1 volt, also called as V set voltage, after giving V set voltage of minus 1 volt, we are getting a change of state from 0 to 1 for this Tsetlin automata MTJ. And similarly, when we are giving the reset voltage as 1 volt again, we are getting a change from state 1 to state 0. So this is depicted in this particular graph. Okay, so that represents the phase 1 and phase 3 here, and phase 2 is the read phase. In read phase, we don't want the MTJ to change the state, but we just want to look at the particular current that is generated from the MTJ. So for that purpose, we give another voltage called VOL. So the difference between these two voltages is sent to the MTJ. So this is 1.2 volt and this VOL is 1 volt. So the difference of these two is zero point 0.2 volt. This zero point 0.2 volt is sent to the MTJ, and the current from it is collected here as some finite value. So we are going to collect all of these currents from every MTJ and every TA, and based on the sum of all those currents will determine whether the particular input satisfy the clause or it doesn't satisfy the clause. So that's the summary of this, and let's also look at the working of this Tsetlin machine inference algorithm. So this picture has in this picture we are considering two literals first, literal 0 and literal 31. So literal 0 is the one that is considered and literal 31 is a don't care thing. So in literal 0, let's just say we are at 0 state for literal 0, then we are getting the output after read as 1. So out 2 is the real output. So which means our clause is satisfying the inputs. So the input might be the particular class, and after we write this particular state to another state, we want the output to change, and output is changing. So instead of being 1, it got down to 0.25 volt, which is near 0. And again we try to change the state back to 0 and then test the output again, and we got the output to be 1 again. So in this way we can, this is the only extreme case, so we show the extreme case. So with this extreme case we can say that our proposed inference architecture is working. And let's now look at the energy efficiency of this particular architecture compared to other architectures of that are based on CMOS Tsetlin machine architecture. So CMOS, this is just the logic gate architecture. So using logic gates, we are getting the average energy consumption for data point as different values for different data sets here. And our work has is quite good reduction in energy for a data point, and you can look at the results here. And these are the results of Tsetlin machine learning algorithm itself. And so So we finally conclude with this. We proposed an inference architecture based on Tsetlin machine and implemented with an MTJ crossbar. The performance of our architecture was evaluated based on energy consumption across various data sets and showcasing its efficiency. Our study offers insights into potential opportunities in in-memory computing using magnetic tunnel junctions for machine learning applications. So the pivotal point of our architecture is the Tsetlin automata. So we are using a 1T1M cell configuration for that, for programming and for reading purposes also. So we conducted a comprehensive evaluation of our architecture, demonstrating its effectiveness in inference through comparative energy analysis using various data sets, highlighting its potential for MTJ-based inference algorithm design. Thank you.